All right, everybody, one last lecture file. You've been directed to watch a movie, and there's a quiz attached to the movie, but some of the questions on the quiz really can't be answered without a few notes from us. So here we've got a few notes. Now, there's normally a lot of demos that go along with this. Unfortunately, I'm not going to be able to play with those right here, but that's okay. We'll make it through some diagrams. So looking at magnets, the movie talked about magnetic fields, talked about planetary aspects of it. We're going to look down at the smaller pieces. So here we've got a bar magnet on the left, bottom right has a horseshoe magnet, upper right is a compass. The compass is really just a bar magnet. That little needle that you see there is a magnet. It's just very carefully balanced on that pin, and it behaves as any magnet would. In fact, early magnets were really just a magnetized needle like that sitting on a cork floating in a puddle of water. So, let's see, we don't play with the overhead, but yeah, we have an overhead projector in our classroom buried in one of the cabinets. We pull it out for pretty much this demo. We'll jump past that. And we're looking at a magnet here. And the idea is if we took a compass, we move the compass around, put it near one end of the magnet, put it near the other end of the magnet, and you saw examples of this in the movie, the compass needle would turn. What it's basically doing is lining up with magnetic field lines. So in the movie, you saw magnetic field lines look something like this. Very, very rough diagram for it. And they liken it to a magnet. So you've got a magnet, you've got a north pole and a south pole. All the pole means is a magnetic field is a loop, and it has a direction. And if we lay a compass down along that magnetic field line, then the compass needle would lay along the line right here, for example, and it would point the direction you see the arrow here. So we'd say the north end of the compass points away from the north end of the magnet. Now that sounds weird, but bear with me on this one. And the south end of the compass would point toward the north end of the magnet. So as we come along over here, say along the equator of the planet Earth here, the compass needle would point toward the south end of the magnet. But wait a minute, compasses point north, right? Well, that's the thing, is the north geographic pole of the planet is a south magnetic pole. The only reason for the definitions is compasses point north. Well, it's the north end of the magnet. The north end of the magnet points north. Well, that must mean that the north pole of our planet is a south magnetic pole. And it's just the way things are named, geographic versus magnetic, and it's how we define the north pole of our planet. It's where the north end of a magnet points. Okay? So, see how these magnetic field lines are loops? And they actually do come out of a side of a magnet as well. If you have a magnet at home and a compass at home, you can actually put the compass next to the magnet, and you'll see it is deflected along the side of the magnet as well. So some weak magnetic field here, strong magnetic fields at the end. The Earth's magnetic field is kind of interesting. It's actually not at the geographic North Pole. It's actually a bit south of that. It's down over in this area if you look at a map or at a globe. And interestingly, it changes position over the course of the day, because as the Earth spins over 24 hours, the sun's energy, the solar winds, they push and deflect the magnetic field. So it actually gets pushed north and south depending on the time of day and where the spot is relative to the sun. So picture being in a boat right here, your compass needle would actually shift over the course of the day. Which is kind of strange. But that's not all. Not only does the field move on a daily basis, it's been moving over time. In 1831, it's down here at 70 north latitude. By 1948, it was up here. Somewhere around 1998 or so, it crossed the 80-degree north latitude. So that's a huge distance. So it's been moving over the course of centuries. And it's predicted by 2050, it'll have crossed over here towards Siberia. So the Russians are stealing the magnetic pole. All right. So you can find these maps online. It just shows the change in position over time, which means if you're navigating by compass, you actually have to know what that change is, what that difference is. And they talked about that in the movie as well. And then the South Pole is also going to be moving, and that shows the position over time for the South Pole, which is the geographic South Pole of our planet, but it's the magnetic North Pole of our magnetic field. One thing about magnetic fields, they're continuous loops. So when you see a diagram like this, it's actually not quite right. The magnetic field would technically be complete. So this line here would actually continue inside the metal. We just can't put a compass there to look at it and measure it. So all of these would be continuous lines. That's how Maxwell's equations all work, is all these things have to be complete loops going through them like that. This gets into deeper stuff on how magnetic fields work. The movie talks something about pretty well, actually better than I will here, so I'll let the movie handle that. And just what some diagrams will look like. Some of your questions on website will pertain to these questions. So understand this is what a magnetic field looks like. It goes out of the north, goes around, goes into the south end of the magnet. If you have a more complex magnet, field will come out of the north into the south, goes through the magnet, comes out of the north, loops around, woo, and comes back into the south, and would go through like this. So complex magnetic fields actually would do something like this. And you'd still have this thing going on as well. That doesn't change. So notice the field coming out of the North Pole here, field going to the South Pole here, they kind of merge together. When these fields merge together, that draws the magnets together. That's why the North Pole of one magnet is attracted to the South Pole of another magnet, is because the field draws them together. If we diagram here, yep, there's more complete diagram for that. If we had a North Pole and a North Pole here, it comes out. It can't go into that other North Pole, so it's going to be repelled by it and come around, come into the South Pole here, complete loop. Same thing here. It's going to come out of the north, get repelled by the other one, come back in around. And since these magnetic fields cannot merge together, they're pushing off of each other. That's why the same poles of a magnet repel each other, because the fields cannot merge. So their fields will look something like that. Ignore this thing in the middle here. This would have to come up and around, because magnetic field lines must be complete loops. So they will go around. I'm going to put a link to this video here. We have these demo equipments in the classroom, which, oh man, we just got them last year, and I don't get to share them with you. It's a shame. They're really cool. But I'm going to add a link to this video, because it's a very, very, very cool video about some very unique magnets that this company makes. So add a link down below for this. All right. Good luck. I'm going to send you another video, just kind of an end-of-year video, so I'll put one of those together. Take care, guys, and good luck finish this stuff up. I'll talk to you later.